Today we will ask some decidability questions about context-free languages. So far we have seen quite a few problems about recursively enumerable languages are undecidable and some are not even semi-decidable. Now I will ask a set of similar queries, similar questions about context-free languages, and it turns out that some of these languages are decidable, whereas some other are not decidable, and in fact some are not even semi-decidable. So first of all, let us formally introduce this problem, what we are going to deal with. Okay, so RE languages are specified by Turing machines, not necessarily total, or by unrestricted or type 0 grammars. Okay, and given a Turing machine M or an unrestricted grammar G, we ask several questions like this, and using reduction or Rice's theorem, we proved that the following problems are all undecidable. Here are some examples. Whether the language of that machine is empty. We have proved that this is undecidable. Whether the language of M is finite. We have proved that this is not only undecidable, it is also not semi-decidable. Whether the language of M is the entire of sigma star, this is also undecidable. In fact, this is just the complement of the first one. Anyway, whether the language of M is context-free, whether the language of M is recursive or regular, these questions are all undecidable. We have seen many reductions and we have seen applications of Rice's theorems, two parts, to prove the undecidability or even semi-decidability of this and many other languages. Okay. Now let us turn our attention to context-free languages. Okay. They are specified by push-down automata or by context-free grammars. Okay. And like Turing machines, a push-down automaton or a context-free grammar, or for that matter an unrestricted grammar too, can be encoded in binary. For a PDA, the encoding would be quite similar to Turing machines. You have to specify how many states, what is the size of the input alphabet, what is the size of the stack alphabet, and so on. And then after this, one by one, you specify the transitions. Okay. Transitions are slightly different from those of Turing machines, but anyway, they can be encoded. Okay. Likewise, you can think that this CFGs or even unrestricted grammars can be encoded. Okay. So now, given such an encoding, which we denote by just a machine M or by a context-free grammar G, okay, we just ask the question whether the language generated by the grammar or the language of the push-down automaton is something similar to this. Okay. Note that this time the issue of decidability is given to a Turing machine, not to a PDA. When we are talking about decidability of certain problems about RE languages, RE sets, it was the possibility or impossibility of designing a decider, and that decider is itself a Turing machine. But in this new context, the current context, we are asking a question about some inferior, I would say, class of machines or languages to be asked, to be answered by Turing machines. Okay, so questions about PDA or CFGs are to be decided not by PDAs or CFGs but by Turing machines. Okay, so we give an encoding of a PDA or a CFG to a Turing machine, and then we ask something like the following questions: whether that grammar generates anything at all, whether the language of the grammar is finite, whether the language of the grammar is the entire of sigma star, and things like whether the language of that grammar is a deterministic context-free language. Okay. So the difference between this and this is that these are issues or questions about Turing machines to be answered by Turing machines. These are issues pertaining to push-down automata or context-free grammars, and they are to be answered by a superior class of machines called Turing machines. Okay. Despite that, Turing machines have better language recognition capability than push-down automata. It turns out that some of these problems are still undecidable. Undecidable in the sense of Turing machines. Okay. Some of these are undecidable, some are not. So with respect to, you would say, RE languages, all these four questions are undecidable. Okay, some are even not semi-decidable. But in the context of context-free grammars, some of these are decidable and the others are not. In fact, we will see that the first first two questions are decidable, whereas the last two questions are not decidable. Okay. So, to start with, let us see an example of a question about PDA or CFGs that can be decided by Turing machines. So that is what is called the language emptiness. Okay, CFL emptiness. This turns out to be a decidable. It is decidable whether a context-free grammar generates any strings at all. That is whether the language of G is empty. For that matter, I can specify this context-free language not by the language of a grammar, but I can also specify an n, a representative n having the same language, and ask whether the language of that PDA is empty or not. This problem turns out to be decidable. So in this lecture, I will give you a couple of proofs that this is the case. That is, in each of these two proofs, I will construct an explicit decider, a total Turing machine, to accept this language. Okay, and reject whenever G or N does not satisfy this condition. The first one is an inefficient algorithm based upon the pumping lemma. Okay, inefficiency doesn't matter for the moment because we are not worried too much about the efficiency of Turing machines, at least in this course, or for that matter in this context. Anyway, so let us see that a decider for this language emptiness problem does exist. Okay, suppose that L is the language of the grammar G, which is provided in the encoded form, or for that matter, I would say, let's say this is a grammar. If a PDA is provided as input in the encoded form, then definitely you may, for example, convert that PDA to a grammar using the standard PDA to CFG conversion rule, and you convince yourself that a Turing machine can mechanically do this conversion. Okay. Anyway, let's assume here and henceforth in this and the next lecture that the context-free languages are provided by context-free grammars. Okay. So let's say L is this. Then it's an easy matter for a Turing machine to find out from the encoding how many non-terminal symbols G contains. Let us call this number N. This can be easily obtained by the Turing machine, the decider, okay, that we are going to construct by simply looking at the encoding of G or a corresponding, okay, G, let's say. Okay, PDA does not have non-terminal symbols anyway. So, okay, then you recall that, of course, we can assume that this G is in the Chomsky normal form. So, if not, you convert it to the Chomsky normal form and then you call N to be the number of non-terminal symbols of G. Okay, whatever. In the proof of the pumping lemma, we have taken a pumping lemma constant to be something like 2 power n plus 1. Okay, which guarantees that in a long path in the parse tree for a string in L, there must be repetition of non-terminal symbols. Okay, whatever it is, let K be a pumping lemma constant. This is an effectively computable constant because N can be obtained. Given N, a Turing machine can easily compute 2 power n plus 1 and this value of K. So this is an effectively computable constant, the pumping lemma constant. Okay. Now what does the pumping lemma say? Okay. Next two assertions are very important for understanding the emptiness problem for the language L. It implies first, if L is finite, then all strings in L are of length less than K. Why? Because if the language contains a string of length greater than or equal to K, then you are eligible to supply that string to the pumping lemma, okay, or to the daemon for decomposition. And the daemon gives a decomposition it is bound to give, right? Because you played the game according to the rules, that is the input string is greater than or equal to K in length, okay. And then you can pump in as many times as you want and you generate infinitely many different members of that language. Okay. So if your language L contains a string of length greater than or equal to K, then it cannot be finite. Okay, it has to be infinite. This is one thing. On the other hand, if L is infinite, okay, then L contains a string of length in the range K to 2K. Why? This is once again an easy, I would say, corollary of the pumping lemma. So, first of all, L is infinite, therefore, all of its strings cannot be of bounded length, like bounded by K. So, pick any string in L whose length is greater than or equal to K. If it is already in the range K to 2K, you are done. Right. Otherwise, if the length of that string that you started with is greater than or equal to 2K, then the pumping lemma will anyway give you a decomposition, and then use the pump out case. You will get a string of length smaller than the length of the string you started with. If that string has length in this range, anyway you are done. Otherwise, you apply the pumping lemma once again, pump out once more to get an even shorter string. Okay. So this process cannot proceed indefinitely. Okay. Because in that sequence of strings, that are in the language L are of smaller and smaller lengths. Okay. Also see that the pumping length is at most k. Therefore, if you start with a string of length greater than or equal to 2k, by pumping out, you simply cannot get a string whose length is less than k. Right? Therefore, it follows that this process of getting shorter and shorter strings, okay, all in the language L, by a sequence of pump outs on different strings, will eventually end up in a string of length in this range, greater than or equal to k and less than 2k. Okay. So that gives me one the important idea about the emptiness problem. Okay. So I can check. Therefore, so these two cases cover all the things. L is finite and L is infinite. If L is finite, then all strings must be of length less than k. If L is infinite, then it must contain a string in the range k to 2k. Okay. And therefore, we can check whether G can generate any string of length less than 2k. So that means we will one by one generate all possible strings of length less than 2k, 0, 1, 2 up to 2k minus 1. And we will check for the membership of each such string in the language. Okay, and we have seen an algorithm for this. That algorithm was not really very efficient, but anyway, it can be done, okay, by exhaustive search, okay, or application of the rules in the Chomsky normal form or whatever. There exists an algorithm. Of course, we have described the algorithm in the form of a pseudocode, something like that, okay. But I leave it to your imagination to convince yourself that this can be done by a Turing machine. Okay. So each such string can be tested in finite time. Okay. In fact, this not only answers the question of emptiness, this also answers the question of finiteness. If you see that there are certain strings of length less than k, but no string in the range, this length range, then definitely this is a finite finite language. Otherwise, it is infinite. So if you detect anything in this range, you conclude that this is infinite. So it not only decides the emptiness problem, it also addresses and decides the finiteness problem of context-free languages, presented in the form of a context-free grammar in the encoded form. Okay. So this is a decidable problem. So the next question is that this is definitely a decider, but this decision mechanism is not really very efficient. Okay. So because you have to generate all possible strings of length less than equal to 2k minus 1, and that's an exponential function in k. So it's not a very efficient procedure, although it doesn't matter. Let us see that a simpler procedure, okay, almost linear time, works for deciding the same problem. Okay. So this is the set of all terminal symbols. This is the set of all non-terminal symbols. I will try to mark the symbols here. So I start with all symbols marked. All symbols of sigma marked. Okay. Start by marking the symbols in sigma, that is the terminal symbols. Okay. Now we one by one keep on looking at the rules. A can be beta, where beta is a string over this sigma union n. If all these symbols in beta are marked, then I mark A. Okay. So if all the symbols of beta are marked, mark A. And keep on doing this. And this process cannot proceed indefinitely. At some point of time, you will run out of elements in sigma union n to mark. Okay. So at that point of time, this procedure stops. Okay. And yeah, so that's the idea. N is finite. Of course, to start with, you have marked every terminal symbol. But then in a loop, you are trying to mark non-terminal symbols one by one. And this process must stop after a finite number of iterations because there are only finitely many non-terminal symbols. And you convince yourself it is a fairly straightforward thing to conclude that L is non-empty if and only if the start symbol is marked. Okay. There are multiple ways of marking S, but if there is a single way of marking S, then L is non-empty, and if S is not marked, then there is no way S can produce a sentence consisting only of sigma, elements of sigma. Okay. So this is a very efficient procedure. So let us see an example how this idea works. So I start with a set of rules. Okay, this is not really a grammar generated from any specific context-free language in mind. This is just for demonstrating how this marking procedure works. So to start with, I mark all the terminal symbols. This is marked, 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 this is marked. In fact, epsilon is marked. Okay, because this can be produced. Okay, so when these things are marked, so I start with this. Okay, this is marked, this is marked, this is marked, these are marked. So I'm showing it in a different color, show that the things that are marked. Okay, then you can see this is an opportunity to mark a non-terminal symbol C because it can produce CC, something. Okay, over sigma. Okay, so I can mark C. And once I mark C, I also mark this, and anywhere else C appears. I don't think it appears anywhere else. Whatever. Marking essentially means, of course, you do not have to mark this in particular. You mark these only. But this side, the markings are shown in order to explain how this procedure works. Okay, so you mark C. Along with that, you mark this, possibly that. That's all. Then you find out if there is any further new marking possibility. Let us see. Okay, you can see that W can also be marked because it can produce epsilon, some sentential form consisting only of terminal symbols. Okay, at present there are no other possibilities, so let me mark W. Once this is marked, I will show this as marked, this as marked, this as marked, but this is just for illustration. Okay, so this is marked, this is marked. Now there are several possibilities. I can mark B because CAW is fully marked, WW is also fully marked, so I can mark B. Or is there any other possibility? Yes, I can also mark U because W is fully marked. Okay, so you can be W can generate something over the terminal symbols only. So I don't know, in this example, what am I doing? Okay, I'm starting with B. So once B is marked, I am marking this B, and so on. Maybe now I take this U, can be W. Okay, so let us mark U and see what happens. Okay, U is marked, and therefore this is marked, this is marked, this is marked, this is marked, so on. Now, let us see. I cannot mark S immediately because A is not marked, V and S are not marked. But this marking has opened the possibility that I can now mark A because B and U, they are both marked. So let me mark A. Then I have this A marked and this A marked and so on. Now you can see that because A, B and C are all marked, I can now mark S. Okay. And that essentially stops the procedure. In fact, you can stop as soon as S is marked, and you can see that V can never be marked. Even if I try to mark V, V cannot be marked, V cannot be marked. Okay. However, although S can be UVS, this rule does not produce any sentential form, which is also a sentence, that is a sentential form consisting only of non-terminal characters, non-terminal letters, symbols. This rule can. Okay. Therefore, I can say that it generates something. Okay. At least one string. Like S can be ABC, A can be AA, or A can be BU. Then I can use U can be W, W can be CAW, and then W can be epsilon. Something like that. Okay. So this is an efficient procedure, much better than the exponential algorithm based upon the bumping lemma. Anyway, so this is a problem that can be decided. In the next lecture, I will prove that in some sense, the complementary question, whether a context-free language is full, that is whether it generates the entire of the input language, sigma star, entire of sigma star. This is, however, not undecidable. Okay, so it is undecidable whether a context-free grammar generates all strings sigma star or not. And as usual, you can specify the context-free language by a representative PDA and ask the same question about the PTA. In fact, we will propose a reduction from the complement of HP to an appropriate language, and this will actually establish that this problem is not only undecidable, it is even semi-decidable. Okay, so a proof for this is not going to be easy. And that reduction, which reduces an instance for the halting problem or its complement to a context-free grammar, is not going to be straightforward. But anyway, in the next hour, we will see how this can be done. For the moment, let us have a break. We will come to a technique called the computation history method in the next lecture.